Okay, my friends, hang on tight. Strange landscape of particles inside a proton mapped like never before. Exactly, you'll see them in a minute. This is on the 12th of August 2023, which is today. Protons and neutrons make up atomic nuclei, are made up of a trio of even smaller fundamental particles known as quarks. Well, I disagree with that. I say quarks are made up of a bunch of fundamental particles called dipole electrons. And that was my theory in electron flood theory. We're writing new books about it and so forth. This goes back to a paper I wrote in 2019. But I've had this theory for many years. I worked on Nike Hercules missile sites when I was in the Army, and after that I was in electronics, and I've been into this my whole life. So I understand what's going on deep down, and the transfer of energy, heat, light. I'm going to show it all to you because we have the evidence for it now. It's not just speculation, not just conjecture like they come up with and trying to figure out what these quarks are and all that. Well, I can show you these particles as light because light is where they want to get down to, is because it's the smallest particle that exists. Light is where they want to be. And what is light made of? Well, I'll show you what it's made of. Okay, before I start, don't forget, electron flood theory says there is nothing but electrons. And this goes back a very long time. But we already built a continuous electron beam accelerator. We've already done this. Now, they're doing this at the Department of Energy. This just came out. The CEBAF is a world-leading facility in the experimental study of hadronic matter. Well, this is way down into these little bits and pieces of quarks, for scientists to probe the interior of the nucleus to study its properties. We've already done this because light is where they want to get down to. So they're trying to build this huge facility now to do the continuous beam. We've already done that. All right, remember this saying, continuous, just keeps going. Electron beam accelerator. They're building this. Now, we already have that, and we did it on a desktop, and it wasn't a lot of money. This is electrons. That little glowy part is an electron. Every time you see the glow, it's an electron. Glow is energy. All right? Electrons create heat, and they also exchange throughout these particles. Electrons are built into protons. So between carbon and nitrogen, I might have already talked about this before, there's literally thousands of additional electrons, more and more, less and less. There's still carbon, there's still nitrogen. Those are called isotopes. They don't even consider those when they're talking about scattering electrons and all that. We need to understand the chemistry that leads to these protons, because these protons are not big chunks. They're just thousands and thousands of little particles in a ball that can be broken up into infinite numbers of different configurations, leading to enzymes and isotopes, all the different exotic electrical particles. You start to get into your CMOS, your complementary metal oxide silicates, you get into all of your different light-emitting diodes, and all of these different field effects. And we have seen them all with this research. That is light accelerating. That is light dividing. The black stays away, the white squirts through, and then the black reattaches over here. That's fission, that's fusion. This is light, and this is continuous beam. We're not trying to hit it into atoms of anything. We're just letting it come through here separated from its dark particle. All right, this is what all of the big particle colliders do. They're taking neutrons and protons, big balls. But they're like this. They're not just solid core balls. All right, they're these. And when they hit, they squirt into all these different things. You're going to end up with photons. That's a photon. You're going to end up with electrons and the other part, which is the dark particles. You've got electron neutrinos and you've got muon neutrinos. So one of them, see the different colors, the red, the blue, the green, those are the, boy, they're confusing it because you can't see the dark matter here. Okay, my friends, look at this. That is a proton, I'm sorry, a photon, oh boy. Okay, I'm going to make this simple. A very young child should easily understand this. They consider these big balls to be solid and have a couple little quarks inside, and they want to break them apart to find out what's inside. So they collide these. Very high speed. Boom! What comes out? All of this debris. And literally it is debris coming from these particles. What does that debris consist of? Well, it actually consists of tiny little dipole electrons. This is 2 dipole electrons back to back. The rest of them are just bits and pieces and chunks of the proton, like the X particles. Then you have your little, neutrinos, and that's a photon. Now let me show you what we did, and I'll show you the particles. They're the same particles. We only use light. We didn't have to bang huge things together. And now that's what they're starting to try to figure out how to do, but we already did it, and it's very simple to do. All right, this is what all of the top laboratories, this is Brookhaven. They say this is a graphic showing a proton moving at nearly the speed of light towards the viewer. So we're looking into this proton coming at us. And these are their basically quarks. The spatial distribution of the momentum of up quarks left, down quarks right, within the proton. Well, let me show you what light consists of. Now, protons are a different story. They may be right, but they want to get down to what is inside these protons. That's what I'll show you, is light. But don't forget, this is where they want to get down to. Continuous beam electron accelerator facility. Now, this is the U.S. Department of Energy. They want to do this so they can get electrons to bombard protons to drive off electrons. You don't need to do that. We can just take the electrons and harvest them, and I'll show you right now. Now, this is Temple. They're all doing the same thing. They're looking for these quarks and the gluons. The gluons are the black and the white particles I showed you. Okay, my friends. Now, I'm not bragging. I'm just telling you this is a fact. They don't take any of this into account. I just talked about isotopes. Well, an isotope means these are all nitrogens. Every one of these is a different nitrogen, but it's still all nitrogen. And they say, well, it has 7 protons. See this Z number? That's the number of protons. N is the number of neutrons. They can't account for these different neutrons, so they just keep making them bigger and bigger and bigger. It's just more and more and more and more and more and more electrons attached to the ball. So this ball right here, okay, this is nitrogen. Well, guess what? I throw about 2 or 3 more on here, still nitrogen. Half a dozen more, still nitrogen. 50 more, still nitrogen. 200 more, still nitrogen. I take 200 off, still nitrogen. They don't even understand how many isotopes there are, because they only find the ones that are stable for a certain number of microseconds or become stable completely. At this number of electrons, nitrogen is stable. It doesn't really want any more. It doesn't want to give any up. But here, it's got too many, and it wants to give some up. They got too many, and the microseconds, they get usually shorter and shorter and shorter underneath nanoseconds, because they're less and less and less stable. The more extra electrons, they want to throw them out of there. That's what radioactivity is. And for life to exist, you need enzymes to break these things down in microseconds. They do more work, an enzyme, in 1 second than it would take 400 years to break a polypeptide bond, which you break them, in your body right now, there's thousands and thousands of them being broken. And it would take 400 years to break it if you didn't have the enzyme. And they snap right off. Those are your amino acids. That's a whole, but this is the key. If you don't understand it all, they don't understand any of this. They say, well, we smash these things together and we see all this trash. Well, big deal. Anybody can do that. You have to understand, what are you dealing with in the first place? How can you explain these isotopes? They cannot. Okay, I showed you this before. Bam! And they see all this trash. Well, the smallest particles they can see are these little red ones, or blue or green. It's a little particle of that. And then they can also see these black particles amongst their mix. And here's what they're actually seeing. And this is actually from Fermilab. This right here. They showed this as a fixed particle. They see these black particles. They have no clue where they came from because they're just in the pile of mix. And then they see these, what they call point particles. These burn. These never change. They're fixed. They're just cold and they just bang things over. These are point particles. They are literally energy, and they can get really big and they can get really small. So could we see these from light? They see them from smashing huge things and getting all that debris I just showed you. Well, if we could just get down to light to start with, this is what we'd get. And this is exactly what we did get. They see these. Remember that little double particle I showed you before? These are gluons. That's a gluon, that's a gluon. Just like two little bar magnets. And this is getting charged up because it's banging ahead going this way. This is behind the black particle, so it's getting smaller. This will get so big, it'll flip. And that one will come in front and start to charge up. And this is what it looks like just in the black and white. But we can see that these point particles, just like Fermilab said, this can get big or it can get small. That never changes, absolutely never changes, and that's a fact. And we separated them right here at the Venturi. We accelerated the light, first of all, by creating a Venturi, which is nothing more than a restriction where all the fields have to crutch each other, and they don't want that. And what it did, it created exactly what they said at Fermilab. It created from the muon neutrino, which is the black part, and the electron neutrino, which is the white part. All right, the black and the white, and these are gluons, the two of them together. But separately, that's a muon neutrino, that's an electron neutrino. You glue them together, and it's a gluon. You take two gluons together, and it's a photon. So these are the photons of light. Zzz! Here it is right here, accelerating. That was just pulse laser, but now it's accelerating and really showing itself, and they're banging against each other because of the reverse. Okay, a little interruption here, but here we're back. Now, don't forget, these are the particles, the black and the white. And here they are separating because the black can't get through this little tiny orifice. They stack up and they squirt the white through like crazy. And the white comes through with a vengeance on the other side. And these are separation patterns. They're not interference patterns where one flaps over this way and that way and so forth. No. Light does not flap. Light spins. The particle here is this particle right here. All right, and it spins. So if we were watching light go that way, we would watch it go spinning this way. If it was coming at us, it would be spinning at us like this. And I can show that actually happening in this pattern right here. They call interference pattern. It's not interference. It's a spin. It's spinning this way sometimes it spins way over this way, sometimes it spins way over that way, sometimes it spins through the middle. There's like a zillion little light particles coming at the same time. There's not just one. From that laser, you can't see them. You see one single wave coming out. This is what it looks like when it starts to accelerate. That's what a laser pulse looks like. Well, what's inside that laser pulse? Is there just one particle? Is there 100? Is it 1,000? I don't know. I can show you there's more than one. And it's starting to accelerate now. That's just a leading tip of the accelerating flash of laser. All of these particles in the air in front are being concussed. They got to get out of the way. This is coming through. They all have fields. These have fields that say, I don't want your field touching my field. Just get away from me. It's called the Casimir effect. So they all have to get out of the way. They glow. Anytime you push something to something else, it glows. And sometimes it hurts. That didn't hurt. I'm just kidding you. But you slap somebody hard enough, it's going to hurt. But that's what's going on here. They're actually getting slapped out of the way. So they're glowing a little bit. And this is glowing more because there's a ball of particles in, not just one. And I can show you that right now. All right, now let's just recap a little bit as I go over this. Now, we saw here that little tiny particle is the photon. You can go back and look at it if you want to see it bigger. And these are what they do at CERN and Fermilab, Lawrence Livermore, all that. They are going to get into electron, acceleration like we're doing. But this is what an electron is. There it is right there. We don't need these big particles. We can start with this because it's laser. And we saw it screwing through the Venturi, and that is the particle making its wave through, and this is the acceleration phase where the particle accelerates and creates all of this enormous interaction at the Venturi, which is right here. And all it is a little slit that comes from here and here. It forces all the particles to converge, smashing into each other. They don't want that. The white says, get away from me. That's what these are. These are repulsion patterns from magnetic fields. So I want your field away, you want, so I'll go this way, you go that way, you go this way, and they stay away from each other. That's what creates this interference patterns. These are coming through this way, spinning, and they're all over the place. You see them here, here. And this one's coming down the center. This one's getting accelerated this way, so it's starting to glow. These are being smashed back because of the explosion. This is literally, and I'm not kidding you, literally a subatomic nuclear explosion. This is what nucleuses are made out of light. And we have separated the particles of light from the black and the white, and they return over here the black to the white. This has to be fission if they separate it, and this has to be fusion if they come back together. In the middle, we should be able to harvest that electrons. Those are 100% electrons, no dark matter whatsoever. This is what you push into a battery. When you charge a battery, all you want in there is electrons. They don't get very heavy. They just get very powerful. If you pushed all the black particles in, they get heavy. The black particles are heavy. That's why 95% of the universe is just dark matter. They didn't realize it was there because it's in behind the white matter. Now what we can do here is if we can just send that laser right down the line, the black stays this way. The white will come through here into what you'd have to have is an electron collector, just electrons. All you want is the electrons. So what you would need is a bunch of these different transition metals, which have all kinds of different energy states. And each one of those can get bounced in by a faster or slower spinning particle. Some of them will go right past the other ones. Some of them will just smack right into them. But if you don't have that energy level receptor, you're not going to get that electron. It'll just go away and you lose it. So we need all these different transition metals. Well, you need a lot of different things, but the transition metals specifically can pick up extra electrons a lot easier than some other particles. That's going to have to be something to really get looked into. But right away, all you need is basically a solar collector, a solar panel, a little bit, more exotic, and then just run that free electrons. When you're getting electrons from the sun, you're getting the full particle. You're getting the black and the white together. All right. Then at the solar collector, you have to divide them, and that's picking up a different type of particle of a molecule that's inside the silicon will accept it, and silicon accepts particles, and then you run it down just like this into the batteries. But this right here, you can carry that around in a. Well, hold on. I have a little thing I'll show you. All right, I'm going to show you something. I think it came from Lawrence Livermore, but I'm not sure. It was one of the big particle guys, which shows the muons being separated from the electron showers, and the electron showers coming through, and the muons all stacking up this way. And this, as the shower progresses, the energy level gets enormous. So again, this is from Fermilab, I believe. It's muon neutrinos, electron neutrinos attached together. They separate at where they hit the heavy water, and the muon goes on its own way. The electrons create showers, and that's what we need. And the showers can increase the energy potentials up into the trillions of electron volts. And this is exactly how you do it. And I even have a little device. Hold on a second. Well, I really don't have it made yet, but it's something that could be made. Okay, this again, the black stays this side. the white, just 100% white electron showers. And this was, like I say, I can't remember, I think it was Lawrence Livermore. And they show, here's the low energy electron showers getting squirted through, and then they get real big. The muons, these are the muons, they bang and they come out, they can't get through, just like I'm showing. The black ones are the muons, and the white ones, in this case red, coming through are the electron showers. Great, enormous amount of showers. Now, you could put this little tiny device, hundreds, maybe thousands of them, inside a little handheld box like this. You carry this around, plug anything you want in. It would be just, hold on, I got it right here. You know, this is just something to show you how easy this would be. That's it. Once it's built and it's made out of solid state stuff, you should be able to bang this around, not have any issues with it. It's all, once you filter out the energy and you get the energy, all the electrons coming down into your harvester device, wherever it's going to be, your batteries or whatever. Probably going to be a battery of some sort. And then at that point, you just redistribute the energy however you want. 220 volts, 110, DC, AC, 50 cycles, 60 cycle, any voltage anywhere. And you carry it around like that. Plug this in. All these fires and all these issues that we're having all over the world now, you're going to have a lot of catastrophes. And we're destroying the earth by burning all these things, making the expansion of the gases enormous. And as we spin through this atmosphere of space, which is not zero atmosphere, I mean, it's just loaded with particles up there. The ionosphere is a scrub of particles. That's where the heat's coming from. Up there it's 2,700 degrees or more, 2,700. And then it comes down to minus 80 degrees. Why? It's the scrub zone, and the opposite of the scrub zone is the cold zone. You're always going to have hot and cold together, and that's what this is. This is all about the nature of the universe, basically. This is where it goes way beyond just looking and banging particles together and seeing all the debris that comes out. And that's all they see is debris. This is what they see. All right, this is what they see. What does that get you? I understand why they see the particles they see and the colors. The colors that are closest to the nucleus are the blue and green. Yellow in that area, white, of course, is all of the real power. Now, when they slam these things together, they take off. The blue goes, never comes back. And that's an electron. The red is already way out around the outside anyway, so it just sort of bubbles around, and it just keeps coming back. Red has very little power, and it's the speed of the spin that gives it the power. One spin is, of course, it's spinning in a circle, but it's going like crazy. That is blue. When it's stretched real out like that, that's red. When it's in the middle, it's green. Those are the chromodynamics. You see that? That's the red laser. It comes in as neutrinos. When they're like an Oreo cookie looking thing with the white in the middle, it's one flavor. It has a certain energy value. Then when they twist sideways, getting more and more concussed against each other. Neutrinos concuss against each other. That's what changes their energy value. It's just the amount of concussion. Once they start to turn into photons, then they're fully formed light particles. Prior to that, they're sort of energy packets that have different values, and that's exactly what they say. They're different flavors. Now over here is the explosion, and they separate. Now the red is slow. Now the green is much faster, but it's exactly the same particle. No difference whatsoever. Same neutrinos, same particle, only a much faster spin. And I can actually show you that happening. All right, here I can show you. This is exactly what happened. The green is much more powerful. You see how glowy that green is? How bright and how fast it's coming in, and it smacks in over here again. The red just gets pushed out of the way. It just doesn't have any power. It's very dull, and it's spinning slowly, and this goes choom, it just knocks it right out of the way. It's the same particle. Now this was done by Fabien Boulez, this particular picture, and he did some light research with us, and enhanced some things, and were very, very nicely done. And I appreciate everything he did. And most everything else was done by Rod Warren. I did very, very little. I did some, but nothing like what these guys did. And Rod spent years and years doing this. So, and this is just incredible. Why can't we take that white before it turns back into the Higgs fields, which are complete particles? They have it backwards. They have the Higgs fields turning into particles. No, the particles turn into Higgs fields. When they recombine, the white recombines with the black, it turns into the Higgs fields. And you see these little white particles spinning out here, and they just spin off and create these little spinning disks, which are the black and the white together. I can't account for that, but it is there. And they know this. They see at CERN and Fermilab and everybody else. But nobody's understood that the particles can separate except the Russians. And I contacted them back in 2015, or maybe it was even before that. When they saw this, they blew out. They blew their minds. During the experiment, we contacted the Earth guys who couldn't believe it either. They saw a big black hole show up in the middle of these charged particles in a vacuum chamber in not quite zero gravity, but almost. That's why it's kind of flat still, because they're still being drawn to Earth. In outer space, where they're way away from everything else, there'll be a perfectly round black hole. But this is what a black hole shows up in their space station. And I understand why, because these are all charged particles, micron-sized charged particles injected into a vacuum chamber. I mean, there's nothing whatsoever in that vacuum chamber, no gases, no nothing. So that comes in, and these are all just charged particles. So they separate the glowy parts, push each other away, and the black parts suck them all in together. So there'll be a crust. And here's the crust forming right now around the dark matter. Nobody's ever understood this before, that these particles could separate. And I didn't believe it. When I first saw it, it freaked me out. Because I know you cannot break a bar magnet in half and have a positive side and a negative side. It doesn't happen. Only happens when you get down to these micron-sized particles, that there's no else no smaller to get to. It's like here, you can't get any smaller. That's light. This is what they want, is light. This is what they're working for, is light. Evidence gravity collapses, Newton's, Einstein's theories, low acceleration. They're coming out with all this stuff all day long, every day now, because they can't explain any of it. According to the standard model, they can't even explain gravity. Do you know that? They don't know why something falls to the ground. Why does that happen? I know why it happens, because the Earth is saturated with these dark particles. The white particles are the electrons that are in the air. They form electricity, which is lightning. It goes right to Earth. Earth is a ground. It sucks these electrons. It wants the electrons. It's that black hole, just like the Russians showed. Static electricity. It gets on you, snap, to water pipe, right into the ground. Why? The ground wants those electrons. Lightning. It's going to find ground. Everything. Light coming to the Earth hits, and it gets hot. The ground absorbs it, and it sucks up these electrons. The electrons are the heat. The white parts are the heat. The black parts just run with them. And I can show that too. Okay, let's bring things up to snuff here. We know we had a single pulsed laser, and this is a measuring laser, and it makes pulses. Some lasers continuously, and they just never stop. This goes boop, 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 boop. Now, that may make a difference in how it interacts with the Venturi. Right now, we have it coming bang, 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 bang. Now, that could be very good instead of a continuous pulse, which may not have the same slapping power. Now, so that I don't know. This is something that has to be engineered. But I do know for a fact that once it hits that Venturi, it separates. The black separates itself from the white. In this particular configuration, Rod had it so that there was no black getting through here whatsoever. None. Zero. Zero blackness. Now, and which created the muons and the electron showers. Now that's where we want to harvest, and this is the kind of interface that I think it would be best. But I can show you that the black is strictly a wave that pushes the white. Now this is really, really interesting. At this one, the Venturi was open just enough so some black could squeak through. And you see the black, that's one little thin strip of black. And then you see all these pulsations, and then you see all these little ripples out in front of everything. Why is the ripples out in front? And then the white is coming behind the ripples, and the black is pushing the white. This is what's going on. The black is literally pushing this wave of white forward because it's been accelerated. You wouldn't normally see this. This is very, 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 very unusual. Okay, this is from CERN, and this goes back to 2021, and this is the physics of electron showers. And that's what I'm showing you. That white is electron showers. They have to use proton-proton collisions, creating huge numbers of this and that, and decaying these hadrons, which they don't even know what they're looking at. And then they want to create these high-energy neutrinos, and then of all different flavors, and then the energy of the neutrinos interacting in this phaser thing they're developing, which is just an enormous waste of money, because all you got to do is harvest them into a photo receiver like I showed, something like this. Very simple. You don't need all that exotic stuff. And then you just, at that point, you're going to have hundreds of gigavolts of electron volts and up to trillions of electron volts. But this is what they want to do, is to accelerate particles, which are charged particles, and then try to separate the charges into dark photons into this phaser. It's not the way to do it. They are going to see the same thing we're seeing. And here it is right here. This is the electron showers. High energy electron showers coming out, and they kept getting more and more as they shower more and more, and they create higher energy showers. The muons, you see the base track of muons? They bang and they just pop right back off. Boom, bang. These go right through. This is what we need to do, is to create these extremely high energy electron showers, put the receiver right there, and let those things go on their own way. Because we can separate them now. I never realized it was possible. Never ever would I have assumed it. But we've seen it. I've seen it in space. I've seen it in our own experiments. I've been touting that CMOS can see these individual light photons for years now, and that's what we used. Back in 2014, we could actually see those same pictures I'm showing you of the light photons. They're just catching up with it now. All right, keep your eye on this. The white particles will come first. Everything will glow like crazy. As you can see, smoke just rises. It doesn't even go anywhere. It just rises. It's not even being pushed. There's no push whatsoever. Now comes the black, which is the push. Boom, there it goes. And everything will turn around and come back. The black has no burn to it. It's just a pusher. Now everything turns around and comes back. All right, don't forget, they're filming this with cameras that are away from the direct exposure, and they're in hardened enclosures, so they're not being destroyed, and they're watching this interaction. Now, this is another one. Here it goes. You see, stuff it's just burning up, just smoking up, and then all of a sudden, the black particles will come and smash the hell out of it. So those are the fixed particles. Now, those are the fixed particles. Bam! All right, that brick held up. All right, but everything's going to turn around and come back. That's the nature of them. Okay, this is from PBS, Spacetime, Public Broadcasting Service. Well, I'm part of the public. And here they come down to atoms. And what it says is that AI, artificial intelligence, prove our proton model wrong. Well, no, I did. Now, they're showing the same thing I was showing, how they're going from cells, which I do the biology too, all the way from cells down to the electrons and protons and neutrons. Well, all there is electrons, and the electrons and muons. Protons, neutrons, all that stuff are made up of those particles. So this is going to be the next next video. I know I went a little long on this one, but this is really very, very important, because if this might even be able to help with the energy situation and help with the climate situation. I mean, it's a pretty serious situation we got going on. And AI, let's see what they have to say, what AI has to say about our reality.